Page 301 we had assigned to us on Tuesday before we did our activity. Our activity, by the way, is due on which day? Friday, right? Handed in on Friday. Tuesday we were working on elastic potential energy, spring potential energy, Hooke's law, so on. We had 5 questions that were assigned on page 301 as a result of that. Is there any of these questions on 301 that we need to go over here? Bree? 5B, okay. Any others? Okay. So number 5. Okay, that works. You know what? I'd rather go over the whole thing anyways than just one part of it, so. Anything else? Okay, let's take a look at number 5 then. Number 5 says, when a spring is stretched 0.4 meters from its equilibrium position. The equilibrium position, by the way, is that position that it's at when it's not stretched or compressed. It's natural position. Okay, here's what it's at when it's sitting on the desk. Well, we're stretching it 0.4 meters from that equilibrium position, so it's 0.4 meters longer than it was. Its elastic potential energy is this value. What's the magnitude of the force required to produce this? And then we want to do something, want to change the force. Hey, listen, whenever we want to change something, let's deal with that later on. Okay, one thing at a time. Okay, question A is not a trivial question. We've got a elastic force, we've got elastic potential energy, we've got a few things going on in there, but we're not changing anything. In question B, we're changing it to a different force. So deal with A, then we'll worry about B later on. We got a displacement here of 0.400 meters in question A. We've got a potential energy here of 500 joules. I don't know why they put that one in scientific notation, to be honest. We want to find the force. The force, we only have one equation that will allow us to find this force, and that's F is equal to K times X. It's Hooke's law, right? Even F is equal to M times A. Clearly, you're not going to use that here because you don't know what an acceleration is. You don't know what a mass is. Clearly, you're not going to use M times A. You wouldn't want to use it anyways. The reason you wouldn't want to use it is because the force changes with the displacement. Okay, if you have different displacements, you're going to have differing accelerations, changing accelerations. Don't go there. Okay, don't go to use F is equal to M times A in the context of elastic potential energy. Okay, it's not somewhere you want to go. The acceleration is changing, so you don't want to use that. It's kind of like saying, look, we don't want to use V equals D over T when an object is accelerating because the velocity is changing. So F is equal to Kx should get us the force, right? We don't know what K is. Any ideas? Don't we usually find K this way by using K times X? We do, right? Usually, here's the problem. We want to find the elastic potential energy. We've got the force and displacement. Get the Hooke's law, Hooke's constant by saying F over X, and then plug it into the elastic potential energy equation. Here, we're kind of working in reverse. Here we've got the elastic potential energy, and we're looking for the spring constant using that. So let's take it over. Let's take the half over by dividing, the x squared over by dividing. K becomes equal to EP over 1/2 x squared. Or you could have said 2 EP over x, either one. We get 500 divided by 1/2 of 0.400. 6,250 is our spring constant, which we're going to plug into here. Yeah. 2,500 newtons. We should be 3 digits, right? How am I going to express that in 3 digits? Good question here. How do I express 2,500 in 3 digits? That's where I got to be here, right? 3 digits here, 3 digits here. Final answer should be 3. Can't say 250 because that's wrong. It's 2,500. But I can't say 2,500 because that's 4 digits. Yeah, okay. Good. You got to put this one in scientific notation. 2.50 times 10 to the 3 newtons. Good. All right, there's question A. That's not a trivial question. Okay, that's a tricky question, a tough question. Let's take a look at B here now. See if it's any tougher. If the force causing the stretch changed to 1,000 newtons, how much change in elastic potential energy results? Well, tell me the one thing that we know for sure 100% stays the same. Good. The elastic constant was 6,250. The elastic constant is still 6,250 newtons per meter. So what are you going to do here? We want to find EP is equal to 1/2 kx squared. Seems easy, right? 1/2 of 6250 times, what's x? What's x? Well, let's use F is equal to K times X. Rearrange it to solve for X. F is 1,000 newtons this time. Remember, F was 2,500. Now it's 1,000. Divided by K, which is 6,250. What's that give me for the value of X? We had a force of 2,500 newtons. Now we're at 1,000 newtons. We know it's going to be a smaller force. Sorry, smaller displacement. What does it bring? 0.16 meters. Yeah. Okay, so let's plug that in here. 0.16 meters, square it. What does that one work out to be? What was it? 80? But that's not the answer that they're going to give me in the book. So what am I going to do here? Yep. Why would you subtract 500 from 80? Yeah? Yeah, I know what you mean there. Yeah, and what are we looking for? Right. The change in potential energy is always going to be final minus initial. A lot of people get to this point here, they solve for this. Okay, they've made it all the way through, and then they get to this, say 80 joules, done. We just didn't quite read the whole question. It asked us for the change in potential energy. We found the final. We have the initial. So let's say final minus initial. It's 80 minus 500 gives me negative 420. What's the deal with the negative there? We can't have a negative potential energy, can we? Yeah, we can have a negative change in potential energy, a loss of energy. We just can't have a negative potential. Is it good?